Hi, hello ib1 higher level students. Next video lesson about relativity, Einstein's theory of relativity. Last lesson was about nature of force. I hope you remember that depending on the frame of reference, the force can be electric or magnetic. Yes, we are talking about simple example with two charges. Okay, traveling with the same speeds in the same direction, and we were analyzing the situation from two perspectives. From the perspective of observer who is outside in the, let's say, laboratory frame, and from the molecule rider, so observer who is related with charges. Yeah, so we concluded that observer A doesn't see movement between charges. From his perspective, charge 1 and charge 2 are stationary, and due to the electric force there is a repulsion between, so force she sees is electric. Okay. In the case of perspective B sees the motion between these two charges. So charge 1, which moves to the right, creates a magnetic field which is directed into the plane of the screen, in this case in the lower part of the charge, and out of the plane of the screen in the upper side of the charge due to the right thumb rule. And charge number 2 moves in this magnetic field with velocity v to the right. So by using Fleming's left hand rule we can state that there is a magnetic force acting acting up the screen. Of course, this magnetic force reduces electric force, reducing net force. But the conclusion is that in one frame of reference, from the perspective of observer A, there is a force, electric force between charges, and in other frame of reference, from the frame of reference of observer B, there is a magnetic force because observer B sees the movement. It's very important conclusion because it states that nature of force is relative. What does it mean? It means that type or nature of force depends on the perspective, depends on the frame of reference. Okay? So today we'll be talking about the Lorentz factor. So something very important in the theory of relativity. We will use Lorentz factor to define time dilation and length contraction, two relativistic effects which are very important in special theory of relativity. And of course we'll be talking about frame of reference. So you can write a topic of today's lesson: Lorentz factor. Okay, remember, you must be prepared to the lesson: pen, pencil, calculator, ruler, your physics notebook, of course, and you must be present on the lesson, as I wrote a message to you. Starting today, I'll be checking your presence during the lesson. You must confirm watching of video lesson by writing a comment below by using your original school's account below in your not in the YouTube channel, not in my channel, but of course in the Google Classroom. Okay, so remember, you have to mark your presence on the lesson by writing a comment below this new video lesson in your Google Classroom. Okay, remember about this, it's very important. Okay, I hope you watched the movie this anime movie about Einstein's theory of relativity. I was talking about this short 30 minutes long movie last lesson last week. Today I'm going to start with this. I hope that you remember that special theory of relativity based on two principles or two postulates. So write point number one, postulates of special theory of relativity, short STR, special theory of relativity. Okay, so special theory of relativity based on two principles. Okay, it's very important because special theory of relativity doesn't work without these two principles. Okay, and first principle states that speed of light in vacuum is the same constant for all inertial observers. Okay, what does it mean? It means that speed of light in vacuum it doesn't depend on the speed of the source or speed of the receiver. But first of all, who or what is an inertial observer? Inertial observer is one which doesn't accelerate. So write this. Inertial observer is one which does not accelerate. So one which moves with constant speed or one which is at rest. Okay, it's very important. So what does it mean that speed of light in vacuum is the same constant for all inertial observers? Okay, it means that speed of light doesn't depend on the speed of the source and doesn't depend on the speed of the observer. Simple example, let's imagine a person, okay, who emits a light from the torch, and second person who receives this light. Okay, if these two people are stationary, then speed of light which is sent is c, which is equal to 3.00 times 10 to the power of 8 meters per second, and speed of light which is received is also c. But if person travels with speed of v, okay, then received speed is also c. It's not like in typical Galilean transformation c plus v. Okay, in this case speeds cannot be added. Okay, speed of light is always the same. In vacuum is equal to 3 times 10 to the power of 8 meters per second. For students who want to know more details about this, you have to read about Michelson-Morley experiment about constancy of speed of light. Michelson-Morley experiment is not part of your syllabus, so you don't need to know this on your exam, but if you want to know more details, please find this in old Tsokos edition 5, because our actual edition is edition 6. In edition 5 of Tsokos you have a lot of details about Michelson-Morley experiment, and of course in internet you can find also a Michelson-Morley experiment about constancy of speed of light. Is it clear? So again, speed of light is the same constant for all inertial observer, which means that speed of light doesn't depend on the speed of source, doesn't depend on the speed of the observer, and in vacuum is equal 3 times 10 to the power of 8 meters per second. Remember, this result was measured many times. Okay? And always is equal to 3 times 10 to the power of 8 meters per second. So this is first principle of special theory of relativity. Second principle of special theory of relativity is fact that laws of physics are the same for all inertial observers. So you know who is an inertial observer, and so now what does it mean that laws of physics are the same for all inertial observers? So let's imagine that there is a person, observer A, who has a ball in his hand, and he throws the ball vertically upwards. Of course, if the ball is thrown vertically upwards, perfectly vertically upwards, it goes up, turns back, and returns to the hand of this observer. Okay, and let's imagine the same situation observed or described by the observer who is moving in the rocket which travels with speed of v due to this stationary observer. So we have the same guy who throws a ball upwards. Of course, due to him, a ball will be moving upwards and will return, and it will be captured by him at the same position. What does it mean? He can describe this situation exactly in the same way as this guy. Okay, why? Because both are inertial. Okay, from the perspective of observer, let's name his A. B moves to the right, but from the perspective of observer B, A moves to the left. So from the perspective B, B is stationary and throws ball staying in the racket, and A moves away from him with speed of v. So this situation is symmetrical. Laws of physics for observer A are exactly the same as laws of physics for observer B. Is it clear? So what is important? That in the case of special theory of relativity, we must use, or other words, special theory of relativity bases on these two principles. First is speed of light in vacuum is the same constant for all inertial observers, and second is that laws of physics are exactly the same for all inertial observers. Okay? You must know these two principles, you must know examples, you must know how to derive these two principles, and you must know that these two principles are very, very, very important in the case of special theory of relativity. So please copy this slide to your notebooks, stop video for a moment, copy this, you will be ready, turn it back, and we'll go forward. Okay, so a few minutes later, yes? Point number 2. A light clock. Okay, what is a light clock? A light clock is a kind of imaginary device. It's something like a thought experiment from which we are able to calculate Lorentz factor, so very, very, very important mathematical formula which describes special theory of relativity. Okay, so what is a light clock? A light clock consists of two mirrors, upper mirror and lower mirror. Okay, and of course distance between mirrors is not important, but let's imagine that this distance is 3.8 times 10 to the power of 8 meters. What does it mean? It means that a photon, a particle of light, which is emitted at time t equals to 0 from a lower mirror, travels this distance exactly in 1 second. Okay, so this is this light clock. Let's imagine a photon which travels this distance. What happens with photon when it hits the upper mirror? It turns. It hits upper mirror and turns. Okay, so photon travels down, and after next 1 second it hits lower mirror. Okay, it's reflected and travels up. So we have something like a clock. So tick is here and tack is here. So something which measures a time is a photon, a traveling photon which hits a mirrors. Upper mirror tick, seconds later, lower mirror tack. And next seconds later, upper mirror and again tick, seconds later, lower mirror tack. Okay? So this is something like an imaginary device. Of course, this distance is not important, because when you will reduce this distance 1,000 times, the clock will be measuring milliseconds. When you will reduce this distance, let's say, million of times, clock will be measuring microseconds. In the case of microseconds, the distance between mirrors is only 3 times 10 to the power of 2 meters, so 300 meters. So now we can imagine these two mirrors at distance are separated by 300 meters, and photon which travels in vacuum between these two mirrors, which hits each mirror and next mirror in time intervals of 1 microseconds. Okay, so this is something which is known as a light clock. So I can write that light clock is an imaginary device which measures a time by movement of photon. Okay, please copy this, write this short description, stop video, when you will copy and you will be ready, turn it back. Okay, so point number 3, a Lorentz factor. So basically, the core of our lesson, of our meeting today. Okay, so we will derive a Lorentz factor based on this light clock. Okay, so let's imagine that you have these two mirrors, a light clock. Okay, and let's imagine that there is an observer inside, a blue one. Okay, who observes this photon which travels a distance between lower mirror and upper mirror and measures this distance. And for this observer, this distance is, let's say, L0, length 0. Okay? Let's imagine another observer who observes the same situation. And let's imagine that for this observer, these mirrors or this clock moves to the right with speed of v. Is it clear? So this speed is observed only by the observer who is outside. So I'm going to mark it by red color because this outside observer is red. Of course, speed is constant, so both observers are inertial observers, or moreover, from the perspective of observer who is inside the clock, from the perspective of blue one, observer who is outside moves to the left. All depends on the perspective. But let's back to the description of situation from the perspective who is outside. Of course, when clock moves to the right with speed of v, then observer who is outside sees the movement of this clock to the right. So let's imagine that in time when photon needs to travel distance between lower mirror and upper mirror, whole clock with observer who is outside and from the with the photon moves to the right. So what is a distance moved by the clock? This distance is speed of the clock multiplied by time which is needed to travel this distance. I said that in this distance photon travels, a photon observed by observer who is inside travels this vertical path. This is distance observed by observer who is inside. What is seen by observer who is outside? Observer who is outside observes the path traveled by the photon as this one. Is it clear? So, from the perspective of observer who is inside the clock, the blue one, distance traveled by photon L0 is shorter than the same distance traveled by photon observed from the perspective of observer who is outside, who sees the movement of the light clock. I hope it's clear. So again, observer who is inside the clock sees distance traveled by the photon as, wait a moment, c's distance traveled by the photon as L0. Okay, observer who is outside the clock, yeah, sees distance traveled by the photon as L. L is longer than L0 because in time when photon travels distance from lower mirror to upper mirror, the clock moves to the right distance v times t, because t is a time a photon needs to travel from lower to upper mirror, measured by observer who is outside, the red one. Okay? So let's use Pythagoras theorem. Yes, this distance, L0 squared, plus this distance traveled by photon in time t, vt squared, is equal to this distance, L squared. Of course, I used this triangle, okay, where this is Vt, this is L, this is L0. Again, L0 is distance traveled by photon observed by observer who is in the clock, so the blue one, and L is a distance traveled by photon observed by observer who is outside the clock, so the red one. So what is the relation between distance and time? So let's look. Light travels, or photon travels, with speed of c, speed of light. Let's imagine that it happens in vacuum. Then speed of light in vacuum is 3 times 10 to the power of 8. But what is the most important? The most important is fact that this theory based on two principles. Okay, first principle says that speed of light is constant for all inertial observers. So we can write that speed of light observed by a blue observer is distance, so L0, divided by time. Okay, and speed of light measured by red observer is equal to L by time measured by red observer. But what is important? If speed is the same, but L is longer than L0, then this t, time measured by observer red, must be longer than this t, time measured by observer blue. So blue measures a different time, okay, than red one. Okay, so blue measures time of travel of photon which is shorter than the time of the same event measured by observer who is outside. And this is amazing. This is one of the consequences of special theory of relativity, that time is not absolute. The time interval depends on the observer, or depends on the speed of the observer. Okay? And something which mathematically links time measured by observer who is inside with time measured by the observer who is outside is Lorentz factor, something we try to derive today, now. Okay, so by using this equation, what is L0? L0 is c times t0. Remember, 0 is related with time measured by observer who is inside the clock. By using this, what is L? L is c times t. Remember, t is time measured by observer who is outside the clock. So let's use these two here. Okay? So L0 is ct0 squared plus vt squared is equal L is ct squared. Okay? So we can write c squared t0 squared plus v squared t squared is equal c squared t squared. We want to find what is the relation between t and t0. So let's move all with t to the right. I'm going to change sides. So c squared t squared minus v squared t squared is equal c squared t0 squared. Or I can write this in the form t squared c squared minus v squared is equal to t0 squared c squared, divide by the bracket, obtaining t squared is equal to c squared over c squared minus v squared times t0 squared. Okay, and I'm going to write this in a little bit different form. I'm going to write this fraction c squared over c squared minus v0 squared in the form of 1 over reciprocal. So 1 over c squared minus v0 squared over c squared, of course, times t0 squared. It's the same because this is something like this raised to the power of minus 1 and again to the power of minus 1. Okay? I'm going to continue here. So t squared is equal to 1 over c squared is 1, and minus v squared over c squared is minus v squared over c squared. And the last step, the square root of this, and we have relation between time measured by observer who is outside and time measured by observer who is inside. And this coefficient of proportionality between these two times, time measured by observer who is outside and time measured by observer who is inside, is known as a Lorentz factor and is described in physics by letter gamma. So Lorentz factor is 1 over 1 minus v squared over c squared. And this something is a something which links, in this case, time or distance measured by observer who moves with time or distance measured by observer who doesn't move. Please stop video for a moment. Please copy this. You must know this. You must know importance of Lorentz factor, and you must know, of course, how to derive this. So stop video for a moment, do this, and when you will be ready, turn it on again, and will be example next slide. Okay, so a few minutes later. So Lorentz factor mathematically is equal to 1 over the square root of 1 minus v squared over c squared. Okay, so let's calculate example. Okay, find Lorentz factor for object which travels with speed 0.8 c. 0.8 c means 80% of speed of light. Okay, so you have Lorentz factor. You don't need to transform speeds to speed of light in standard units to 3 times 10 to the power of 8. You can write this in the form of, except v, you have 0.8 c. Remember that in the equation is squared divided by c squared and square root of 0.8 squared is 0.64, c squared is c squared divided by c squared. You can cross c squared. 1 minus 0.34 is 0.36, and the root of 0.36 is 0.6. My powerful calculator says that 1 over 0.6 is equal to 1.67. So Lorentz factor is equal to 1.67 for this particular example. Okay, look on this. What is the conclusion? Conclusion is that for small speeds is 1. Okay, so if speed is really small, like, I don't know, your car speed, 100 kilometers per hour, or your PE teacher who is running 8 meters per second, maybe 9 meters per second, yes? You don't need to take into account this relativistic effect. For these classical situations, speed is constant. Okay? But when speed increases, yeah, then this v squared over c squared is closer and closer and closer to 1. So 1 minus v squared over c squared goes to 0, which means that this also goes to 0, which means that this goes to infinity. So in the limit, when v is very, very close to c, then Lorentz factor is very, very close to infinity. So what is the shape of graph? How Lorentz factor depends on the speed? So right, next point, probably point number 4, Lorentz factor versus the graph. Okay, now task to you. Take your powerful calculators, okay, and plot this graph. You have to plot a graph Lorentz factor on y-axis versus v on x-axis, taking c equals to 1, yeah, and you have to limit your v to the range between 0 and 1, okay, and scale your graph in the case of x from 0 to 1, in the case of of y from, let's say, 0 up to, let's say, 10, okay. Then you please stop video for the moment, make a list or make a graph how this depends on this. So basically, again, you have to plot a graph y equals to 1 over the square root of 1 minus x squared over 1, and you have to limit your x to 0.1 and plot a graph in the range of 0.10 in the case of y. Okay? You have to obtain something like this. So this is your v measured in c, this is 1, this is 0, Lorentz factor cannot be less than 1, so we have two asymptotics for y equals to 0 and for x equals to 1, and you have to obtain something like this. Lorentz factor is very, very, very close to 1 in a long time, and then it increases rapidly up to infinity if v is closer to c. Okay, so this is your solution. Okay, I hope you like this lesson. Your homework is easy. You have to read in your Tsokos, okay, about Galilean transformations and why do Galilean transformations work? Why don't Galilean transformations work in the case of high speeds? Okay, and you have to find something which is called Lorentz transformations and read this. Especially in the case of speed or velocity addition. How to add velocities or relative velocities of two objects traveling with their very high speeds by using Lorentz transformations. This is your homework. Okay? I hope you like this lesson. Any comments or suggestions, write as the comment for this movie, or write to me via Google Classroom. Learn physics, stay at home, remember relativity is very, very exciting. So see you in the next video lesson. Bye.